thanks a lot. And then, yeah, nice to see everyone here. And then thanks a lot for inviting me here. So my name is Jia Yuan, and then I'm currently a member of technical staff at Amazon FAR, and then soon will join UPenn as assistant professor. So today I'm going to talk about integrated learning and planning with neuro-symbolic concepts. So I want to start from this broad question of how can we build general purpose physical intelligence, that is some system that can perceive, can understand in language, that can take actions in the physical world. So one of the options to approach this giant problem is you think about intelligence as fitting functions to some data sets. So for this kind of physical intelligence, you say, I want to build a policy pi that maps from my historical observations to the next action to take. And then to build that, you collect some data sets, by teleoperation or different kind of techniques. And this is taken by a lot of the companies here in the West Coast. For example, this is a video released by a company called Physical Intelligence, training their robot to fold boxes. And then to solve this particular task, you need 100 hours of training data just for folding boxes. And recently, people have been, in order to show the generality of such kind of approach, people have been trying to deploy such kind of system on excavators. They're training their system to generate, joystick commands to control an excavator to do some task for them. And this is, the original Twitter post, but I want just to, highlight one of the sentences from it, which is, in order to get, here's our first demo, we'll collect 200 demonstrations for that, simple, I would say, excavator kind of a manipulation tasks. So overall, we have seen a lot of success of kind of, data fitting kind of approach, but overall, they still have, low data efficiency, meaning that you need a lot of data to learn a relatively simple task as appear to a human. And also, they have limited multitask performance. That is, usually this policy is only, optimized for solving one task pretty well, but lack the generality. So I want to make a contrast between that kind of paradigm with, what humans can do. I would argue humans can learn from one example and generalize reliably to different states and different goals. So again, looking at the excavator as an example. So let's just watch this video. Okay, a very smart trick of manipulating some objects on the, on the ground. I guess you probably have never seen such kind of manipulation before, ever in your life. And despite that, you might not be able to, actually operate an excavator, this, 5-ton machine. But I assume everyone could already get some idea about this. And you can probably, after some practice, you can also solve it yourself. Right. And another dimension is, generality or, generalization to different kinds of goals, right? So if you think about house cleaning job, you're constantly facing different kinds of goals, incorporating different kinds of objects, and you can still, solve all of them. And here is another example showing, how generalizable human manipulations are. So this is a physical game that you can play yourself. You have a bunch of objects on the table, and you pick two of them, holding them one with each hand. And in this case, the cap and the pen. And the task here is you want to pick up a third object from the table without using your hand to touch them, but use the tool that you're currently holding. So this is a trial by a human, trying to use a pen and a cap to lift up a glass. Right. This is probably a task you have never seen before ever in your life, and probably something they would never seen after, never want to solve ever in your life. But, by just looking at this situation, you can already make some plans internally, and then by watching other people showing it to you once, you can make a trial yourself and adapt, and eventually maybe solve the task very competently. So I would argue what we want for robotics is some system can match this level of human level performance. That is, they can learn from very few demonstrations, some new capabilities, and then being able to generalize across different kind of scenarios. So in today's talk, I'm going to show you some of my work aiming at a new paradigm for solving such kind of problem, trying to achieve building AI that can learn from very few demonstrations on the order of 1 to 10 and generalize reliably out of distribution to novel states, to novel objects, and to novel goals. The central idea here is to combine machine learning and policy learning and everything with planning. So it starts from this high-level view of thinking about physical intelligence as a combination of world modeling and planning. So if you look at this thing, as humans, you not only see the pixels or patches. What you see is that, first of all, there are objects there. And objects, they have properties, they have shapes, poses, materials, and so on. And you not only understand the state in such kind of an abstract way, you also understand different actions. Starting from the current state, you can say, what are possible actions that I can do in the current situation? You can say, okay, if I push the glass slightly to the left with my pen, what will happen? Basically, you're able to enumerate possible actions that you can do, and also imagine before execution, imagine what will happen if you take the action. And such kind of paradigm, you can use with a search-based algorithm, trying to get a plan to eventually solve the task. So this idea is, when you're facing a task, instead of, saying, I'm directly following a policy, but instead what you have is a world model, that is, how you model, what are the actions that you have, and then what are the outcome of these actions, and do a planning with them. So I would say the key idea is to plan with such kind of compositional abstraction of states and actions to solve the problem and to achieve the generality. And you will see later what I will call such kind of compositional abstraction over states and actions, neuro-symbolic concepts. So, all of this is a bit abstract, but now I'm gonna, talk to you about, the details and then more the technical contents about it. So the entire talk is outlined as follows. I'm gonna first introduce some basic ideas of neuro-symbolic action models with applications in one-shot skill learning. And then we're going to add, more reasoning into it about, in the language space and about spatial reasoning with applications in more complex instruction following. And then finally, we're going to talk about how we can build neuro-symbolic planning compatible action models with applications in long horizon plan. So now let's get into the first part. So I want to start from talking about how should we model an action. So for example, for a simple task like pick, I want to pick an object, I want to pick an entity using one of my hands. So how should we really represent the body, the content of it, right? One of the straightforward approach is you say this is a policy that from your current state to the target action, and if you follow that policy, you will be picking up the object. But there's one limitation of this kind of approach or issue. If you look at this previous example of using two tools to pick up a third object on the table, you can say, okay, let me try to use 3 separate skills or actions to achieve this goal. The first one is pick up the pen, pick up the cap, and then pivot the glass, and then pick it up. The issue is the particular way that you pick up your pen actually should be dependent on how later on you want to pivot the glass, because not grasping pose of the same pen of the same cap would work if later on you want to pivot the glass and then pick it up from the table. So this means that if you learn those 3 policies completely separately and directly just execute them one by one, you will not be able to solve the task. What we call this is they cannot be directly stitched together to solve the final task. So this is one of the limitations. That is loose, is loose of compositionality. So another option to think about action generation is you think about action generation as a constraint optimization. So again, for the simple task of pick up a plate from this kitchen counter, you can say, my goal is to generate trajectories that satisfy, first of all, some path constraints. I want to have my robots stay within my joint limits. I want to avoid collision with other objects in the environment. And then I have some sub-goal constraints, like eventually I want to be holding the target. What this formulation brings us is now you can compose multiple actions because it's basically adding up the constraints temporally and spatially. So, for example, if you want to, pick up the plate and then place it onto the rack. Again, you have the same set of like a path constraints. You want to stay within joint limits. You want to avoid collision. And you have the first sub-goal, which you want to be holding the target. And then second of all, you want to have the plate on the rack. And mathematically, this can be written down as a constraint optimization problem saying I'm giving you the current state, which composed of the drawing position, the object position, and so on. I want to find two trajectories, T1 and T2, and two states, S1, S2. Minimize some cost, let's say the total length of my trajectory, subject to the dynamics of the system. Like starting from S0, if I execute T1, I'm reaching state S1. And then if I execute T2, I reach state S2. Other constraints like my trajectory should be collision-free. Other sub-goal constraints, like I want to be holding the target. I want to continue holding the target while I'm moving to the rack. And then finally having the rack on having the plate on the rack. So all those constraints can be categorized into several categories. Some of them are rigid body dynamics. Some of them are some geometric constraints. And some of them are more task-relevant constraints. So what this view gives you is that now you can think about learning could happen in two different levels. You can say, in order to learn how to accomplish the task, the first step is I want to learn what are the set of constraints I need to follow in order to solve this task. And second of all, how can I generate those trajectories or states or grasping poses or those continuous values that will satisfy those constraints? And we'll soon see, what is the usage of this. And another thing is now some of those constraints can be modeled with human-built models. For example, for rigid body physics, we can just use, physical simulators for them. For some geometric constraints, we can use motion planner to find solutions to them. We don't have to learn everything from data. And only for the important thing, like those task-relevant pieces, we're going to learn them from data. So I want to ground all those, things in a concrete example. Let's say we want to learn how to hand an object from a single example. So let's say this is a demonstration that I'm giving to you. Someone is, picking up this hanger and put it on a rod. Now I want to generalize this skill to a complete unseen situation, where the task is to put the mug onto the mug tree. And here, this problem is challenging because if you think about this as you want to pick the grasping pose on the target and then a hanging pose of the object on the mug tree, and then really those things are jointly constraining each other because not every grasping pose, for example, if you're grasping the mug from the handle, then there will be no space to put that onto the mug tree. So this is a very classical, robotics manipulation problem. A lot of the approaches have been, proposed to solve this problem. One of them is you just rely on model-based planning. That is, kind of like a search over possible trajectories for moving the object, and then until, you find a successful path. But this is very slow. A more modern learning-based approach is, operates as the following. You do some unsupervised learning and some policy learning afterwards. Usually the idea is that you collect a large data set of possible mugs, and you train some geometric feature on top of it. And then based on this feature, you train another policy that generates the robot actions. Okay, but first of all, the performance is still, not really satisfactory. And then second of all, you really need a lot of data for, different kinds of mugs. And it does not transfer across category very well. So based on the frameworks that we had before, now we can decompose the problem into two parts. The first set is that we want to learn, in order to solve this hanging task, what are the set of constraints I need to follow? This is equivalent to detecting what is the sequence of contacts that I need to make between my robot and different objects. Like in the first step, I want to make contact with the mug, and then I want to have the mug having a contact with the mug tree. And second of all is, how can I compute what are the contact positions I need to be making contacts? So our solution to this problem is we're doing a constraint optimization with visual correspondence guidance. So on the top left, there is the demonstration, and also I'm highlighting the point that is the contact point in the demonstration. This is what you need is you want to say, if I want to manipulate the target object, what is a similar point on that target object so that I should make contact on, right? It's like, for example, looking at the hanger position, like what is the corresponding functional points on the target object would have the same affordance. And this can be solved with a lot of different approaches, and the particular approach we're using is we use some pre-trained visual feature, and then we compute the visual feature correspondence there. We're using Dino V2 in this particular case. But this is not enough because, if you visualize this, heat map of, what is the most probable point to make contact, it's very noisy, and a lot of the proposals are wrong. So you should only use this as a guidance and then verify them with a model-based planning to go through the entire, motion planning and, grasping analysis and then stability analysis so that you can make sure what is the good contact points. But this gives you like a gigantic speed up over a blind search baseline that is, you're enumerating randomly sample possible contact points on the object. And this gives you, this one-shot generalization to those novel scenario, like picking up this mug and then place it onto the mug tree. And then, of course, here we're relying on some models to do some heavy lifting for us, including we use model for 3D reconstruction. We use a physical simulator to help us to, test if contact is stable or not. And this generalizes to other kinds of, mugs and also different kind of kitchenware. This is another very interesting, result that I want to show. Like we 3D printed some, alphabetical shapes, and we say, okay, hand those alphabetical shapes onto the mug tree. And then, this is a nice set because, first of all, they look very different from, mugs or from, hangers that I've seen there. But also they have a lot of like a diversity in terms of geometric structure, right? And you can see our model, is deciding on, where they want to pick up and then where to, to place to hand. You can also benchmark this. If you say, I do, one-shot, policy learning, if you stress test it on this, like, completely unseen alphabetical shapes, the performance is like 0. Of course, if you have more demonstration, it will be better and better. If you do some, use the visual correspondence using the visual feature to help you to do the policy learning, you get slightly better performance, but still far away from perfect. And our model overall gives you over 90% success rate on this particular test bed. So to quickly summarize, we have been talking about this idea of doing one-shot learning of generalizable actions, which is, we can learn from one or very few demonstrations and generalize to different kinds of objects in different kinds of situations. The principle here is we are combining neural representations to give us some guidance about, functional correspondence and physical models to do, the stability analysis, this kind of thing for us within this constraint optimization framework. By integrating them, and then we get the best of both worlds, which is both efficient and generalizable. So the approach that I've been talking about so far can also be extended to slightly longer horizon manipulation tasks too. So here I'm teaching my robot using 2 sticks to rotate an object on the table and push it and lift it up, and then each with just one single demonstration. And now I ask the robot to operate on a new scenario with completely unseen target. This is like a different letter, and pick it up. And then the model is automatically generalize individual skills and then compose them together to finally lift it up. So this is kind of similar to the ABC pickup, but also in a very constrained setting, like all the objects are relatively simple and then they are rigid, but still some initial sign of life about how far or how generalizable this kind of approach can go. Okay. So far, all of those demonstrations have been, relatively short horizon. We have been talking about, a few objects making contact with each other. Of course, if you want to have, more general purpose robot that can work in your household, this is not sufficient. So we need to add more to the system. And in the next part of the talk, I'm gonna briefly mention how we can extend this framework by integrating some more machine learning components. In this particular case, diffusion models, to help us to do some spatial reasoning. We're looking at a particular, manipulation problem, which is setting up tables. Okay. So suppose that I'm giving you this language instruction. Let's say, let's set up a breakfast table, and then there's no snack today. And then this is what you would expect, from the robot. And this problem is challenging because, a lot of time you would have to learn from these humans, preferences, and also you have limited data for this kind of problem settings, and they're relatively long horizon. If you want to, set up a table, it usually takes, minutes of manipulation. And there are a lot of variabilities. So if you use the same tool, which is, constraint optimization, trying to think about this problem, you can say the problem is essentially, I want to find the object poses that satisfy some constraints. That is, some spatial constraints among each other. In this particular case, let's say, our goal is to, given the shapes of different objects, like the apple, the plate, the spoon, and everything, I want to find the pose of each one of them, subject to, the apple is on the left of the plate, the spoon is on the right of the plate, and then, maybe the mug is next to it, and then something else. And this can be, better visualized in a graphical kind of a structure. That is, I want to find the pose of all these objects, which subject to, some constraints among each other. So again, if you formulate the problem in this particular way, now you get the leverage. Now learning can happen at two levels. You say, I want to find the set of constraints I need to satisfy if I want to set up a table following humans instruction. And it is worth noting that a lot of those, what are the constraints, like which object should be placed on the left of which, is actually common sense knowledge. So you can actually leverage those, pre-trained large language models or vision language model to help you to, to learn those kind of, to output those kind of common sense knowledge instead of learning everything from robot demonstrations. So the entire system work like the following. So starting from some language goals and some initial image containing all the object shapes, we have a vision language model that generates what we call an abstract spatial relationship graph. That is, for each individual objects, what are their spatial relationships, and we have a finite library of possible relationships, like left, right, horizontally aligned, vertically split, or things like that. And then during this synthesis procedure, you can also provide additional examples showing what is your preference. For example, we can say, okay, so I come from a Chinese family, so I can say I give you some examples about how my family usually set up our dining table. And after that, we use what we call a compositional diffusion model, which I will introduce in the next slide, to actually generate the pose of all the objects. And then subsequently, how can I control my robot to move the object to the target pose? Here, I don't have enough time to talk about the details about this graph generation procedure, but at a high level, we are using some program synthesis technique to generate the layouts. Now I want to dive into this compositional diffusion models, which takes as input this graphical structure, which is totally symbolic, and it generates continuous values, in this case, the pose of the objects. How do we do it? For each of the relationship we have, for each kind of the relationship, for example, left, we have a dedicated model, a diffusion model trained on it. So for people who are not familiar with that, you can think about diffusion model takes as input, the pose of objects, the shape of objects, and output an energy value. Sorry, by the way, this is not like a class, this very standard formulation of diffusion model, but I will soon talk about, what is the relation between them. But for now, for a minute, think about there's a scalar energy function that quantifies how well does my input, which is the shape and the pose, satisfy this constraint, which is A is left of B. Okay. And then if you look at the original optimization problem, you can write it down as a minimization problem. That is, given the shape of objects, you want to find the pose of objects, which minimizes the summation of all the energy functions over all the constraints that you have. Okay. And in practice, this diffusion model is not exactly predicting, the energy value, which is a single scalar, but they're predicting the gradients over the inputs so that, if I move this object slightly to the left, then it will be more subject to, A is left of B. So in practice, those things are predicting some gradients of, over the inputs. And then we can basically combine those diffusion models by adding up those gradients to solve the original problem. So here's a visualization of it. So this is what a gradient field or an energy field would look like for a linear diffusion model. So for example, if you say, I have my diffusion model for, near front edge, then this means that, when you're close to the edge of the table, your energy value is lower. And then you also have the gradients pointing towards, the closer to you, to the table. And then for other kind of constraints, like this one is left of the other, this one is right of the other, you have different kinds of energy fields and the gradients. And the optimization takes in place where basically you add up all those energy landscapes together, and then also the gradients all together to form a new composed field. And then this is one of the example. And from there you find the minimum value, or the value that minimizes the energy function, and which gives you the position of the target object that you want. And then I'm skipping a lot of technical details here, but the particular technique for us to draw samples from it is called, unadjusted Langevin dynamics. And then we actually have some proofs saying that, our method is more simplified from actually sampling from the target distribution, but it's an unbiased sample. You can take a look at the paper to see more details about the mathematics behind it. But a high-level idea is that once you have trained, individual models for each individual kinds of, relationships, now, for new set of relationships, you can just compose them at inference time without additional training to generate placements of objects. And this approach could work in a lot of different diverse scenarios. For example, for study desks, for coffee tables, for dining tables. And we also managed to do real robot execution by integrating additional motion constraints. So for example, in this case, we have our robots, we have like two arms actually, set up on both sides of the table, and then each robot actually has their own workspace. So when you're planning, you also need to take into consideration the motion constraints of these robots. Like the left robot can only put objects on the left-hand side of the table. And then we have a bunch of assets for the robots to set up, and then the robot first synthesize a plan that is subject to all the motion constraints of the robots, and also all the geometric constraints, the spatial relationships that is predicted by the large language model, and then we can execute them. This is accelerated video, but eventually can set up the table for you, and you can give it diverse set of instructions, and then they can follow. So here I'm showing you a very simple extension by extending the previous constraint optimization framework with more machine learning components, in this particular case diffusion models, so that we can achieve learning from field demonstrations and then generalize to new things and a new kind of like a spatial reasoning tasks. The principle here is we're composing neural diffusion models within this neuro-symbolic constraint optimization framework. And we're leveraging large language models for some common sense knowledge. And of course, currently I'm primarily showing you examples in spatial reasoning, but of course, the same thing could be extended to diffusion models of actions, of trajectories, and so on. Okay, so far our reasoning is still about about spatial, but in order to really solve long horizon tasks, you need to reason about things temporally. So therefore, in the next part of the talk, I'm going to talk about neuro-symbolic planning compatible action models. So let me clarify the problem setting we're looking at here. We're trying to do learning to solve long horizon planning. Let's say we have some data, which is in our case 10 demonstrations about a particular task. In this case, pick up the dishwash. The dish soap, and then do some pouring, and then clean the plates, and so on. And each demo here only show you how to wash a single plate. And our goal is to make long horizon plans with different kind of obstacles or even different kind of plates, in a similar scenario. This is one of the example. where we are asking our model to, watch 2 plates and then sort them on the rack. So this one particular aspect makes this task challenging is because you actually need to reason deliberately about in which order you want to watch these plates, because the movements of the further away plates will actually be blocked by the initial position of the first plate. So your model cannot say, I just in arbitrary order, watch these 2 plates and put them onto the rack, but I need to actually think about if the space allows me to do it. So how can we achieve this? The high-level idea is we want to use language to help us to make sense of long horizon planes shown in the demonstration. So again, starting from some demonstration video, the first thing we do is we're using video language models, back in the days Gemini, to help us segment the entire trajectory into several segments. And each segment, they will also give it some action name, like this one is picking up, that one is adjust or something. And then we'll be using some vision models to help us to segment those point clouds, those raw observations into 3D point clouds so that I can do future learning on. And then what this gives you is, for each step in your demonstration, you can say here are all the relevant objects involved in each individual step, and then you get the trajectory of those object point clouds. And of course, your robot hand too. So what you get if you have a data set like that, for example, 10 demonstrations, is a few demos on the order of 1 to 10 for each individual skill or each individual action, like a pickup you want to learn. So because we want to do planning, we not only need to know how can we execute a task, but as I briefly mentioned before, I also need to know what will happen if I take this action. So basically, each action will be modeled in 2 parts. The first part is what we call the trajectory constraints. That is, how can I generate a trajectory that will pick up the object or place the object? And another one is, what is the state? What is the future state? Like where the objects will be after I execute this action. So to operationalize this, what we have is, we have the input to the trajectory constraint satisfaction model is the initial position of the gripper and also, the object point clouds. And then we train a diffusion model on top of it to generate, possible trajectories. Some of the time it's placing the book on the left, some of the time it's placing the book on the right. This depends on, what is the data coverage you have in your demonstration. The second piece of model takes the initial state, like, the gripper position and the original point cloud, and also your inferred trajectory to predict what will happen in this particular case, where those points will be at after I execute this policy or execute this trajectory. Of course, additional, other state changes like, this is vertical aligned or some other things could be also incorporating this model. But here, let's just focus on, the geometric parts of it, like how the object pose will change. Now, giving a new scenario, let's say I want to place this book onto the shelf. What I can do is that I can first come up with a high-level plan, or what we call like a task skeleton, that is, a sequence of actions you wanna take, but without deciding what is exactly the trajectory you need to execute. And you can internally simulate, if I take this particular trajectory, what will happen? For example, if you adjust this pink book, towards the left, then, the pink book will be rotated, and then it will be, touching the left-hand side of the shelf. You can also, enumerate, the next action based on this state, saying, okay, after that, if I place my book following that trajectory, will it succeed or not? Right. In this particular case, it will fail because now the point cloud of the book will now be colliding with the point cloud of that clock. So this is not a feasible plan. So due to collision. So now this means that you need to try, a different possible trajectory. And then in this case, let's say this time you sample a trajectory that is placing the book on the left. And then, this time it succeeded. And you can execute it. First, pick up the book from the table. Push the pink book towards the left. And then finally do the insertion of the new green book. Okay. So what we really stressed here is the generalization of such kind of policy. In particular, we are training our policy on the following scenarios. First of all, all the objects, they are kind of like axis aligned. They are kind of like a well set up table. And second of all, at the most, the two books is like the total height of the books are 2. And we are testing it in various different kind of scenarios, including new heights, like there are more books, new different, position or orientation of different objects. These are, different, XY position or, different orientation of things. And also, in scenarios with novel obstacles you have never seen before. And you can see our model is capable of finding plans in all different kind of situations, where if you directly train, a policy model that solves the entire task end to end, it's not able to do it. And we have more comparison in the paper. Here is an extended version of the, the mug tree hanging experiment that we see in the very beginning of the talk. So here we're collecting some data to hang different kind of mugs onto this mug tree. And then we have 10 demonstrations per mug. And then, but for each demonstration, you only hand the mug, only hand one of the mugs. But now if you have to hand all the mugs onto the mug tree, you not only need to, be proficient in hanging a single mug, but also need to make some plan about, where those, like which mug should go onto which branch, right? And also the order of them, so that you make sure that a future hand mug won't be colliding with the existing mug. And our model is, making some deliberate plans about this and then, execute them in the physical world. And then here's another example, having, different kind of, different set of mugs in different initial states and so on. Okay. So what I've seen in this part of the talk is we enable, future learning of action models and then use planning to, combine them together, by using trajectory samplers to sample possible trajectories and then using our transition model to predict the future before we actually execute them and then select what is the best sequence of action to act. And then the advantage of such kind of system is, again, you can learn from very few demonstrations and then generalize reliably to a wider variety of different situations. Here, the principle here is we're composing some neural trajectory generation models using, very similar framework as, the diffusion models we talked about before, and transition models also learned within this neuro-symbolic planning framework. And then, to put those things in, more modern, words, it's like we're combining neural trajectory generation model with world models to help us to do the planning and then, select the best plan. And also here we are leveraging, large vision and language models to do a lot of heavy lifting for us, including, segmenting objects, segmenting relevant objects, and also teaching you some common sense knowledge, but all at the symbolic level. But put that into the learning framework to make learning more efficient and then put the planning more generalizable. So overall, in today's talk, I've been talking about this idea of, neuro-symbolic concepts. And we are talking about, learning and planning with neuro-symbolic concepts to enable more data efficient learning, such as, learning actions from a single or very few demonstrations. And with generalization to completely unseen objects and states and possible goals. So someone might argue, okay, so all the examples that are shown here are, in relative, low data regimes. Okay, so now in the era of foundation models, should I ever still care about this? I mean, or will this problem just be natural outcome of, large models with trained on larger data? So before I really end, I want to, give some of my self-reflection on how I think about this kind of framework of like a neuro-symbolism in the era of foundation models. And I will show you, why this kind of idea is still very, very important and actually very useful, especially for academic research. First of all, so far I've been showing, neuro-symbolic more like a, algorithmic framework to help you to achieve some particular application. But there's a lot of scientific aspects about it. Basically, neuro-symbolic system provides insights into the scientific understanding of tasks and learning. What do I mean by that is, using this kind of framework allows you to not treating your data or your task or your model as a black box, but it gives you, insights, lens into it, such as you can analyze using very similar related techniques that I just talked about in this talk to analyze the expressiveness of big neural networks, including graph neural networks or transformers. And also you can talk about, for a problem, let's say I want to learn to hand or I want to learn to wash dishes. How hard are they? You can talk about the circuit complexity for those models, and then they will also have impact or have implications on how much data do you need in order to train such kind of model, or is it even possible to train such kind of model that can be to be very capable for the task using a finite amount of data. This is what we call like identifiability problem in machine learning. And also, robotics is not just like a simple machine learning problem, but eventually it will become a system engineering problem because due to, data availability and also latency reasons, just simply, any practical robot system should be a compositional system, that combine of, high-level planning, lower-level, control, and so on. So neuro-symbolic systems provide, a principal way to think about the integration of all different pieces, including perception, memory tracking, planning, and control. And recently, we're, building on some of the insights we got in developing some of our past systems. We're releasing, open sourcing this new framework called, Retriever. It's a programming model for closed-loop robot agents. And then it is based on the principle of you want to have asynchronous robot action, and also you want to do time-explicit typing. That is, for each of the modules, for example, high-level modules or low-level control modules, you want to explicitly annotate what is their control frequency and, how they should be, composed together. And this is a demo that is, playing at, close to, to real speed of a system that is able to make plans, long-run plans where the task is to, season the stick, and then also track memory. In this case, they're searching in different drawers to find the target. And then finally, having robot action control. And all those things are, they're only 2x playback. So this, our system, because it was asynchronous execution and the task, and then time explicit typing. So it's really, really efficient and also very smooth. Another thing is, now we have, better and better, foundation model for all different kind of tasks. Like we have, better computer vision models, language models, and, also, action models. Now it become more and more important to compose different kind of systems with principled algorithms for, of like probabilistic reasoning or planning, compared to just like a simple chain of thought. So what do I mean by that is, so far in this talk, you have been looking at, I building, here are the features that I care about. I'm learning some action models for hanging, for grasping, for, washing plates, and I'm composing them together using some, search algorithm or inference algorithms. If you scale this up, you can imagine what it would need is what we call like a model orchestrator. That is, tell you what are the set of constraints or what are the features, what are the action models you would care about in a particular environment. And also having models that can recognize object states, that can generate possible trajectories, and so on. So, for example, giving, this is the context, like I want to wash this plate, and then I have, models that can tell me what are possible states, features, and action models that I should care about. And then for each one of them, I could have, models that can take as input my sensor input, and then, some concept that I care about, and generate different kinds of outputs, like a Boolean label, or, a pose, a trajectory, or even forces, and so on. And for robotics, one thing I'm really excited about is how we can build novel paradigms for training such kind of a model from diverse kind of data. So, for example, if you think about like object detection or classification, you don't necessarily need robot action data to supervise on it, right? But at the test time, you can say all these models can be composed together using a principled neuro-symbolic reasoning algorithm, such as constraint satisfaction. And this is analogous to, nowadays you heard a lot of this word called like agent hardness, right? So you have like a different agents that can do different small tasks, but you still need to have a system that can really compose them together to solve a more complicated task. And neurosymbolism gives you a lot of, insights into how to design such kind of system. And finally, about data. So actually, raw data as we all know, is very, very hard, very challenging to collect. So, and another perspective to put it is we really hope we can have continual learning capability of some self-improving models for task generation, planning, and policy learning. So what do I mean by that is, currently most of the demos that I show, no matter, how generalizable they are, they still say human provides some data to the system and then they learn from it very efficiently. Now it can solve more problems. But what we really hope is you start from some basic computational systems, basic computational foundation models. Now you use the reasoning and planning and maybe, exploration algorithms that you have developed to get new capability and then to get new experience in the world. And hopefully these can become, the data to train the next generation of foundation models, which will then become, the basis for the future iteration. With that, this is a framework that you can really, starting from the basic capabilities, like, basic capabilities for recognizing objects, for, pick and place, for some other, small skills, and then really explore yourself and then find new capabilities and then, refine your model further and further. So again, this thing is already happening, I would say, in, for example, agent research or in just, vision language model research, where people are composing different kind of foundation model with different kind of capability, but distill the knowledge into each other to get, even stronger capability. For example, starting from a vision language model that can only give you labels for an object, given some conversation history, and a model that can do segmentation, for example, segment anything models. You can distill the knowledge into each other to get a model that can support promptable segmentation. That is, you can give it arbitrary text instructions, and then it can give you, language segmentation maps. So overall, I've been talking about this framework that I've been building in the past about neuro-symbolic concepts to enable, more data-efficient learning and, better generalization. I would say this is a new bet for generally intelligent systems, which, really bridges our understanding of intelligence, that is, how we think about the modularity of them, how we think about the fundamental hardness, the complexity of them, and leverage those insights into our building process to build, better and better systems. So with all that, I want to, thank all the funding agencies that funds, most of these projects during my PhD study, and my advisors and collaborators, and also some of the mentees of mine during my PhD who contributed to this work. With all that, thanks everyone for listening. I'm happy to take questions if there's any. Yes.
I'm wondering, for the common sense knowledge at symbolic level, do you think it's infinite, or do large language model, foundation model today have enough common sense knowledge at symbolic level?
I think it depends on what do you mean by a symbolic level, because you can also describe fine-grained geometric things with a super long kind of paragraphs. I think I would say we're still far away from leveraging the full repertoire of existing semantic knowledge in those large models in robotics. We're still far away from having that as a bottleneck for us.
So in the example with the blocks being placed on the shelf, you mentioned that future states were being generated, predicted from the algorithm. And I was wondering how were those future states evaluated as successes or failures?
By evaluation, do you mean how do we evaluate the quality of them? Do you mean how were they predicted?
like how did you determine that that was like a successful, like desirable end state? Or like not?
Oh, I see. Yeah. So that particular, in that particular system, what we do is we're using a vision language model to help us to generate a task skeleton that we know can achieve the task relevant part of it, and then the future state prediction is only handling the physical feasibility parts, like there's no collision and things are stable and things like that. So basically, again, there's a, they do different work. Like the vision language model is using all its semantic knowledge to talk about some task goal kind of like level understanding, and then the transition model we learn, and so the trajectory is more handling the low level control part. We're making sure everything is physically feasible. Yeah. Sorry, what is the diffusion policy? Oh, because what you need is you need a model that not only generate a single possible trajectory to do this task, right? Because if you want to put a bunch of let's say sort a bunch of books onto the bookshelf, right? You need to say here are possible ways or possible places that I can place the book, right? So basically, you need a probabilistic model of possible trajectories or possible target poses, and that is modeled with a diffusion model. Yeah.
Yeah. The book example, the robot could have put the clock away and kept the book. So
yeah, that's possible.
Yeah. There are these secondary byproduct effects that maybe are some are desirable, some are not. Mm-hmm. How do you think about maybe either during or after the fact building the model to figure out why it did either verifiability or figuring out that it's not learning the wrong thing or the thing you don't want it?
Yeah, that's a very good question. Yeah, so by the way, sorry, I'm not sure if people over the internet can hear the questions, but the question was in the task of putting books onto the bookshelf, another option is that you can remove the clock from the bookshelf and then place the book at its location. And then the question is how can you verify or make sure that the model is choosing the correct behavior or the preferred behavior, right? This is a very good question, and then we didn't do much of exploration in this particular work. One thing that I would say is possible is you can say human preferences are just additional utility functions that you should factorize into the overall planning framework, right? For example, you can say, okay, while I'm placing all those books, I would prefer to put them together next to each other, other than spread it out over the entire bookshelf, right? And then that is actually another important reason why you want to have such kind of compositional system where you have learned to generate the possible book placement poses and trajectories, but at inference time you can factor in additional constraints from either user preferences or additional physical constraints and find a solution that simultaneously satisfies all of them. And then that's one of the possible way to implement that. Yes. Sorry, please.
Yeah. Thanks for a great talk. So I'm wondering, what's the, I guess in terms of planning time, so are you guys planning like an open loop trajectory and then execute? So do you think it's possible to do it in closed loop, or it takes too long to plan?
Actually, in this particular video, what we're showing, it's already closed loop execution in the retriever example, where there's some model doing some high level planning for us, which is operate at, for example, 0.5 hertz, 2 seconds per iteration, and then some like a memory tracking system that is operating at 1 hertz, and then but all of those systems are still keep predicting, keep adjusting based on the new observations that I get from the environment, right? So for example, here, after observing that, after opening, let me go back to the beginning. So after opening the the left drawer, actually didn't see the chili pepper, right? So I know I need to update my memory and also my plan to explore a different drawer, right? So all those things are executed in the closed loop, and in the previous work of like sorting books, we didn't do that closed loop execution, but it's definitely possible to do it. And then previously we wasn't able to do that is because if you want to actually do them like asynchronously, there are a lot of like engineering challenges because different modules actually operate at different speeds, and then they need to sync up the states together. And then that was a challenge with standard sequential programming models, and that's part of the reason why we developed this new framework to do this. Yeah. More this.
I maybe. Sorry. Amazing talk, by the way. I was just wondering for like this specific experiment, did you have like a simulation environment that you were testing, or how do you if we wanted to test something similar, what is the best way to benchmark?
Yeah, the question was for this particular demo, do we have corresponding simulation experiments with it? Yes, we do have not exactly this particular thing set up, but similar things set up in the simulation so that you can also run roll out the system in simulation. Yeah.
Is it just on this website?
Yes. Okay.
You did not say, I was curious, you didn't say very much about the neuro aspect of why this is neuro-symbolic. Can you enlarge a little bit on that?
Yeah, the question was like, what is the neuro aspects of this? So basically, in basically all the works that I've been talking about, there is a symbolic structure that is helping you to structure, what is your reasoning process? Like, I want to find values to satisfy all this set of constraints. Right. Let's say some of the constraints are about geometry, like avoid collision. Some of the constraints are about, task, like I want to have the object at a particular location, or I want to have this object stably hang at a particular location, right? And then the symbolic part is all about that graphical structure of that constraint graph. And then each individual, let's say, edge of that graph is associated actually with a neural network because you need neural network models to help you to generate, object poses or grasping poses or, contact points that can, satisfy those constraints. And the important thing is that overall, these neural networks do not operate on themselves. Like, I make my prediction, you make your prediction. But overall, they are integrated together, saying I want to have values that simultaneously satisfy all the constraints. And then that is, what the composition inference algorithm does. Yeah. Great question. Thanks.
Yeah, I think we have to wrap up the board, but